Hello everyone. Today we'll be looking into a chemical engineering gate question from GATE 2020, question number 44. An elementary liquid phase reversible reaction P reversibly giving Q is carried out in an ideal continuous stir tank reactor operated at a steady state. The rate of consumption of P minus Rp is equal to Cp minus 0.5 Cq, where Cp and Cq are the concentrations in mole per liter of P and Q respectively. The feed contains only the reactant P at a concentration of 1 mole per liter, and the conversion of P at the exit of the CSTR is 75% of the equilibrium conversion. Assume that there is no volume change associated with the reaction and the temperature of the reaction mixture is constant throughout the operation. The space time in minutes of CSTR is dash rounded off to 1 decimal place. So this is a question from Design of Ideal Reactors, and the reference NPTEL lectures can be found in Module 1, Lecture 17, Design of Mixed Flow Reactors, Chemical Reaction Engineering 1, Homogeneous Reactors by Professor K. Krishnaya, Department of Chemical Engineering, IIT Madras. So in this question, they have given, so the rate is given as Cp minus 0.5 Cq. So they have also given us the initial concentration of Cp, which is Cp0, as 1 mole per liter. Other data that they have given is that the conversion of P or Xp is 75% of the equilibrium conversion, which is Xeq. So Xp is equal to 75% of Xeq. And we need to find the space time of the reactor tau in minutes. So one thing, they have also mentioned that there is no volume change and the temperature is also constant. So using this, let us see what happens at equilibrium. So to find the equilibrium conversion for this question, for this reaction P reversibly giving Q at equilibrium, we need to know that the conversion Xp will be X equilibrium, and also the rate of the reaction minus Rp is equal to 0 at equilibrium. So we'll use this data minus Rp is equal to 0 at equilibrium to find the equilibrium concentration. So let us equate the rate equation to 0. So Cp minus 0.5 Cq is equal to 0. Then we can solve this equation and find the equilibrium conversion. So rearranging, we'll get Cp by Cq is equal to 0.5. So this is a constant volume system. So we can write Cp and Cq in terms of their initial concentration as Cp is equal to Cp0 into 1 minus Xp. And here, since we have equated it at equilibrium, it will be Xp equilibrium. And Cq is equal to Cp0 into Xp at equilibrium. So basically what this means is Cp, the final concentration of Cp is nothing but whatever fraction that is remaining after the equilibrium conversion, and Cq is the fraction that got converted from P to Q at equilibrium. So that is how we get these two equations for Cp and Cq in terms of their initial concentrations Cp0. So Cp0 into 1 minus X equilibrium. So now we are just equating this Cp and Cq using their initial concentration and equilibrium conversion, and we'll get this equation Cp0 into 1 minus X equilibrium by Cp0 into X equilibrium is equal to 0.5. We can cut Cp0, Cp0, and we can get the equilibrium conversion. So X equilibrium will be equal to 0.667 or 2 by 3. So this is the equilibrium conversion. Now they have given that the actual conversion is 75% of equilibrium conversion. So XP is equal to 75% of XEQ. So that means XP is 75% of 2 by 3 or 75% of 0.667, and that will be equal to 0.5. So 0.5 or 50% is the actual conversion of P that occurs in this reaction. Now let us use this conversion and the data given to us, and let us write down the design equation for CSTR. And using the design equation for CSTR, we can find the space-time tau for the CSTR. So the design equation for CSTR will be tau is equal to Cp0 minus Cp by minus Ra, which is the reaction rate, which is minus Rp here. So now all we have to do is just substitute all these values for Cp0, Cp and minus R, or the rate of the equation, and we can find tau. So to find Cp, we know that Cp is equal to Cp0 into 1 minus Xp. We just found out that Xp is 0.5. So it is 1 in, and Cp0 is 1. So Cp will be 1 into 1 minus 0.5, and that is 0.5. So now we have Cp0, we have Cp, and we have the equations for Rp, which is Cp minus 0.5 Cq. So to complete this equation, we also need to find Cq. So for Cq, we can use this same. So Cq is equal to Cp0 into Xp. So that means 1 into 0.5, that is 0.5. So we have both Cp, Cq. We also have Cp0 and Cp. Now substitute all these values in the equation for design equation for CSTR, and we can find tau as Cp0 minus Cp by minus Ra, which is Cp0 minus Cp by Cp minus 0.5 Cq. And now substituting everything, tau is equal to 1 minus 0.5 by C 0.5 minus 0.5 into 0.5. So now simplifying this, we'll get tau is equal to, or the space time tau is equal to 0.5 by 0.5 minus 0.25. So that means it is basically 0.5 by 0.25, and that approximately comes to 2 minutes. Thank you.